So now we move on to the second question of the tutorials on root locus. The second question is, let g of s equals minus k into s plus 1 the whole square divided by s squared plus 2s plus 2 with k greater than 0. The same figure 1 is followed here. Now the first part of the question is, find the range of k for closed loop stability. So we'll go to the solution part. The characteristic equation is given by 1 minus gh equals 0 here, because this is in the form, this negative is there, so it will be in the form 1 minus gh equals 0, which corresponds to a positive feedback system. Okay. Now the condition k greater than 0 is given. Now from the characteristic equation we can form the route array. So 1 minus k into s squared plus 2 minus 2k into s plus 2 minus k equals 0. So after forming the route array, the s square coefficient is 1 minus k, then s square row is 1 minus k, and the alternate coefficient is 2 minus k, so it is written here. Then for the s row it is 2 minus 2k, and for the s raised to 0 row it is 2 minus k. Okay, now if all are positive in the first column, then 1 minus k greater than 0, 2 minus 2k greater than 0, and 2 minus k greater than 0. So if 1 minus k is greater than 0, that means it's k less than 1. Then 2 minus 2k greater than 0 means again k less than 1. 2 minus k greater than 0 means k less than 2. So k less than 2 and k less than 1. So basically the condition is k less than 1. Okay, k less than 1. But in the question it is given that k greater than 0. So k is in between 0 and 1 for all positive in the first column. So this is one condition. The range of k for stability is either this one, 0 less than k less than 1, or what can be the second condition? If all are negative means you can form the route array with k minus 1, 2k minus 2, and k minus 2. Then k minus 1 greater than 0, 2k minus 2 greater than 0, k minus 2 greater than 0. In that case, you will get 2 less than k less than infinity. Okay. Now, going to the second part of the question. Sketch the system's root locus. What's the system's root locus in this case? So let me first take the conditions for real axis. Which all segments of the real axis are part of root locus here? We have two zeros at s equals minus 1 and two poles at s equals minus 1 plus or minus j. Okay, at s equals minus 1 we have two poles, and for if we solve this particular equation s squared plus 2s plus 2, this one equals 0, then we get the poles at s equals minus 1 plus or minus j. So these are the poles and these are the zeros. Now we have only zeros on the real axis. Now I am supposing that I'm plotting the root locus for 1 plus dh equals 0. 1 plus dh equals 0. Then I'm going to invert the root locus to get the plot for positive feedback 1 minus dh equals 0. So initially I'm doing for this. Okay. Now there are even number of poles here, even number of zeros here on the real axis, right? So if it is 1 plus dh equals 0, the condition is if the system is a negative feedback system, 1 plus dh equals 0, then to the left half side of the zeros, if you see, that is not a part of root locus, because to the right side it is even number of poles and zeros, right? Basically it is zeros only, but they are zeros only, but here it is even. Okay. Now to the right half side of the zeros, these two zeros, it is 0, right? Number of poles and zeros is 0, but 0 is taken as even. It is not taken as odd. So this is also not a part of root locus. So for 1 plus dh equals 0, the whole real axis does not come under the locus. Okay. So when you convert this to a positive feedback system, it becomes 1 minus dh equals 0, and you have to invert it. So wherever the in whichever segments on the real axis the root locus is not a part of, those would be the part of root locus in the inverted root locus. So basically the whole real axis will come under the root locus plot, is a part of root locus plot, in the positive feedback system. Or you can use this rule. The rule is, instead of following the odd number of poles and zeros, we have to follow the even number of poles and zeros. The rule in which even number of poles and zeros to the right side is considered. So here you can see 2 zeros are there. So this is an even number of zeros, right? So to the left side it is there. This is a part of root locus. Now to the right side it is 0, right? Number of poles and zeros is 0, but 0 is taken as even. So this is also a part of root locus. Basically the whole real axis will come under the root locus. So now we got the parts of real axis which are which are a part of root locus plot. Okay. Now to find the complex conjugates, the branches leaving from complex conjugate poles, we don't know it is in which, we don't know the direction, right? We have to find the direction. To find the direction, either we can go for the analytical method or you can go for the graphical method. So suppose if you are going for the graphical method, then this is your equation, theta d, angle of departure equals 180 minus phi, which is phi, where phi is sigma phi p minus sigma phi z, where phi p is the angle contributions from poles, and phi z is the sum of angle contributions. Sigma phi z is the sum of angle contributions from zeros. To get that, what we are going to do is we are drawing a line from this pole to the other pole, right? Other pole you are drawing. So this angle is 90, right? This angle is 90 degree. Okay. Now, so this is basically the angle contributed by the other pole. Only one pole is there other than this minus 1 plus j. Now we draw this, the line segment to 0, right? 0. So here 2 zeros are there. So 290 degrees are there, right? So the contribution, the total contribution from zeros is 180, right? 180, right? 180 degree. Now, this sigma phi p is 90. This sigma phi z is 180. So 90 minus 180 is minus 90. Now 180 minus 90 is 270. So the angle of departure is 270. Angle of departure at minus 1 plus j is 270. 270 in the sense, this is 90, this is 180, this is 270. So this should be the line, right? This should be the line. So this is for 1 plus gh. This is for 1 plus gh. So if the branch leaving from minus 1 minus j is symmetric to this branch, then this should be like this. This branch should be like this, right? Will be like this. This will be like this. But for 1 minus gh, we need inversion, right? So when this is inverted, this will become like this, and this will become like this. So this is not there. Okay, so basically our root locus will look like, from here it goes like this, from here it goes like this. These are the zeros. The whole real axis will come under the root locus. Okay, so that's how we plot the root locus for this particular question. Now, what is part C? Find the position of closed loop poles when k equals 1 and k equals 2. Obviously, we know the closed loop characteristic equation here. From the closed loop characteristic equation, it's a quadratic equation, and solving S will give you minus b plus or minus root of b square minus 4ac by 2a, in which this expression will contain k, right? So k values are given. It will, after simplification, it will be minus 1 plus k plus or minus root of k minus 1 by 1 minus k. So you can substitute k equals 1 and k equals 2. When k equals 1, the poles are at infinity, and when k equals 2, the poles are 0 and minus 2. So that's all for today.